This video is an introduction to functions. Now you might be thinking straight away, how is this going to be an introduction? We've already done functions a lot in GCSE and in Year 12. We've used that word function a lot in our lessons and we've seen this sort of notation before. The problem is I've been a little bit imprecise with how I've talked about functions previously. I've always just said that they are a rule where we substitute a value of x in and we get a value of y out. We're going to see in a moment that it's not quite as simple as that, and we need to be a little bit more precise with what a function is exactly. We're going to talk about the domain, which is all of the x values that a function can take. I say x values here. It doesn't necessarily have to be x. It could be t if we're talking about parametric equations, for example. So the domain are the input values. The way I remembered that, domain's got an in on the end there, so domain, input. We're going to look at restrictions that might need to be applied to the domain of a function. And then we're going to look at the range of a function, which is all of the y values that a function can give, or the output values. So first, the formal definition of a function. A function is a rule where every input in the domain gets mapped to a distinct output in the range. So the key words there are underlined in bold. Every input gets mapped or turned into a distinct output. So informally, I can summarize that by saying that every x will get turned into only one value of y. Let's have a look at a few examples that will hopefully help me explain that a bit better. So here I've got two functions and one mapping that is not a function. The first one, f of x is equal to 2x plus 1. Every x value I choose here, whether it's 1, whether it's 2, whether it's 3, whether it's a half, whether it's minus 1.5, I can substitute all of those x values into my function. So every x value will get mapped, and when I substitute each x value in, I will only get one y value. One x value gives me one y value. Therefore, we call this a one-to-one function. It is a function because it satisfies this definition where every x value gets mapped to only one distinct y value. The second function that we've got here is the cubic equation. G of x is equal to x cubed plus 2x squared minus 3x minus 1. Again, I can substitute every x value into this cubic expression. There's no restrictions on which x values I can substitute in here. I can substitute any number in here. And when I do that, I will only get one y value. So for example, if I was to substitute minus 1 in, I get 3 out. Only one value out. If I was to substitute minus 2 in, I only get one y value out. If I was to substitute a half in, I only get one y value out. The other thing for me to state about this function Watch what happens when I substitute -1 in. And I'm not quite sure what this decimal is here, but roughly, let's say -1.6. So I'm substituting two different values of x in here. X has been -1 and x has been -1.6. I'm substituting two different values of x in, and I'm just getting one y value out, the 3. That's okay in terms of the function definition, because every x goes to only one y, and there is only one y in this case, the 3. But there are two different x values that go to that. So two different x values go to one y value, so that's why we call this a many-to-one function, because there are many x's that go to one y. Now, the third rule I've got here, sine y equals x. That is not a function. And it's not a function because it fails the definition on two different counts. First of all, every x. Well, I can't substitute every x into this rule. For example, if I substituted 2 in and said sine y equals 2, well, there are no real solutions to that. Sine y can't equal 2. Remember, sine is only going to be between 1 and -1. It can't equal 2. So it fails the definition because I can't substitute every x value in. It also fails the definition on the second count as well. Because let's say that I said that x was a half. So a half on my graph is roughly here. And there is one solution here, which we know would be 30. Sine 30 is 1/2. But there would also be another solution here at 150. Sine 150 is 1/2. There would also be another solution over here at 390. Sine 390 is also 1/2. So for the x value of 1/2, there is many different y values. There's 30, there's 150, there's 390, and so on. So every x value does not go to only one y value. So this third example, sine y equals x, is not a function. Right, let's talk about domain restrictions. Remember, domain is the values of x that I can substitute into the rule. Now, what I've written here, f of x is equal to ln x. That is incorrect as I've currently written it. Because remember, a function has to be so that I can substitute every x value and I get one y value. But currently I can't substitute every x value into ln. Think about what the log graph looks like. The log graph looks like this. It is only defined for positive numbers. I can't substitute 0 in. I can't substitute negative numbers in. Remember, that comes from the fact that the logarithm, ln, is basically saying what's the power. So it's basically saying e to the power something equals, well, it can't equal 0, like I said. You can't have 2.718 to the power of a number and get 0. It can't equal negative numbers either. the logarithm is only defined for positive numbers. Therefore, the way I've written this right now, this is not a function because I can't substitute every x value into it. But what I can do is I can restrict the domain, so restrict which x values I can substitute into this so that it does become a function. So if I said f of x is equal to ln x, but x has to be greater than 0, so me putting this restriction on the domain over here, that's now telling the reader that x here has to be bigger than 0. And therefore now every value of x that's greater than 0 can be substituted into this. I will just get one value of y. So this is now a function. The second example, f of x is equal to 1 over x. Right now, this is not a function because there's a value of x here that I can't substitute in. I can't substitute 0 into this expression. If I tried to substitute 0 in, I'd get 1 over 0, 1 divided by 0, which is undefined. I can substitute any other value of x into this, but not 0. So I'm going to restrict the domain by saying that x can be any real number, but it cannot be 0. This symbol here means belongs to. This means the set of real numbers, so all real numbers. So this is just saying x can be any number, but it can't be equal to 0. And again, by me adding this into the function definition here, I have now turned this into a function because I now can substitute every value of x in the domain into this function. Third example, f of x is equal to root x. Again, right now this is not a function because there are values of x here that I can't substitute in. I can't substitute negative numbers in. I can't do the square root of a negative number and get a real number. So I'm going to restrict the domain by saying that x has to be greater than or equal. It could equal 0. I can do the square root of 0, but I can't do the square root of negative numbers. So by restricting the domain, by saying that x is greater than or equal to 0, I can now substitute every value of the domain into this rule, so it is a function. There's two other reasons why the domain might be restricted. It could be restricted for the purpose of inverse functions, but we'll talk about that when we do that lesson in a couple of lessons' time. Or we could have an artificial domain restriction, which is not strictly necessary for the function definition, but might be there for other reasons. And we'll see an example of that in a minute. Right, let's talk about how we can find the range of a function. Remember, the range is the set of y values possible. So we're going to do this by 3 steps. We're going to sketch the function using either graph transformations or using your calculator, and there'll be another video to go along with this one about how to do it on your calculator. We're going to consider the domain, and then once we've sketched it, we're going to have a look at the y-axis and think, what's the smallest value of y? What's the largest value of y? And then we're going to write that down as an inequality, saying that f of x is greater than the smallest value and less than the largest value. You could use y instead of f of x if you prefer. And we need to consider whether it could equal either the smallest value or the largest value as well. So we're going to do 4 quick examples. Here's the first one. I want to know the range of y equals x squared minus 4x plus 2. So first of all, I want to draw a sketch of this. I know it's going to intercept the y-axis at 2. So let me put that here. I'd like to know the turning point of this, so I'm just going to complete the square quickly on this, so I can find the turning point, which is going to be at 2 minus 2, which is roughly here. I'm now going to sketch my quadratic in. That will look something like that. So I've sketched it. I'm now going to consider the domain. Now, this is an artificial domain restriction. It's not strictly necessary for the purpose of this function. I can substitute any x value into here, so that this domain restriction is not strictly necessary, but it is here for this question anyway. And I only want to look between x being 0 and x being 5. So x being 0 is here, which means I'm not really interested in this part of the graph, so I'm actually going to rub that out. And where x is 5, which is roughly over here somewhere. So again, I'm going to rub this part of the graph out. So here's my sketch on the domain. I'm now looking to see what's the smallest value of y and what's the biggest value of y. So we start off with y being 2, we go down, 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 down. When we get to this point here, that is the smallest value of y here, which is minus 2. We then go up, 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 and then we get to the biggest value of y over here, which I don't know what that is just yet, but I do know it's when x is 5. So if I substitute 5 into my original function, 5 squared minus 4 times 5 plus 2 is 7. So that's telling me that the y values are always between minus 2 and 7. So I can now say that the range of my function is f of x is going to be less than 7 and greater than minus 2. Now, it can equal minus 2, so I am going to put a line underneath there. I know it can equal minus 2 because that happens when x is 2 and x is allowed to be equal to 2. I am not going to put a line underneath the 7 though. That would be wrong because the 7 occurs when x is 5. And looking at my domain, x is not allowed to be equal to 5. So this is my range of that function. Next example. Now this is an example where you wouldn't be able to use your graphical calculator for this because we don't know what a and b are. So this is one you're going to have to do with graph transformations. I know what e to the power x looks like, so let me draw that to begin with. E to the power x looks like this. It has a y-intercept of 1 and it has an asymptote of y equals 0. If I then times that by a at the front, that's going to stretch it by a scale factor of a in the y direction. So it's going to get a times bigger. So it's now going to have a y-intercept of a because of the 1 times a. The asymptote will stay the same. It will still be y equals 0 because a times 0 is still 0. And then when I add the b to that, that's going to shift the graph up. B squares in the y direction. So my asymptote is now going to become y equals b. My y-intercept is going to become a plus b. And from there, we can hopefully draw the rest of it in. And it will look something like that. So So now we've drawn that, let's think about the range. What's the biggest that y can possibly be? What's the smallest that y can possibly be? Well, the smallest, I can see down here, it's getting closer and closer and closer towards the b asymptote. It will never equal b, because it can't touch the asymptote, but it will get closer and closer towards b. The largest value, well, it goes up and up and up and up forever. There's no upper limit to the range in this question. So my range is just simply going to be f of x is greater than but not equal to b, and I don't need the upper limit, so I'll leave that blank. And that's my range. F of x is greater than b. You could write it the other way around if you wanted to. Third example. We've got 2 to the power minus x minus 5, where x has to be greater than 1. So let's start off with graph transformations. I'm going to start off with the 2 to the power x graph, which I know looks like this. We've got our y asymptote, our horizontal asymptote of y equals 0, and it's going through the point 0, 1. If I put a minus on the inside there, that's going to reflect it in the y-axis. That's now going to look something like this. Then, if I subtract 5 from that, that's going to move the whole graph down 5 squares in the negative direction. So my new y asymptote is going to be y equals minus 5. The new intercept is going to be 1 take away 5, which is minus 4. And it's going to look something like this. So I've drawn a graph, but we've got a domain restriction here. So x has to be greater than 1. Well, 1 is roughly here on my graph. So I'm only looking at where the x values are bigger than 1. So I'm not really interested in any of this part of the graph over here at all, so I'm just going to rub this out. And this is the only bit of the graph I'm really interested in. The smallest value of y, where I can see this green line's getting closer and closer and closer towards minus 5. It will never touch minus 5 because it's the asymptote, but it gets closer to minus 5. So that's the smallest value. I can say that f of x has to be greater than minus 5. The biggest value that y can be is this value here. I don't know what that is yet, but I do know it's when x equals 1. So if I substitute 1 into the original equation, that's going to tell me the y value, which is minus 4.5. That is the biggest it can be. It can't equal it. I'm not going to put a line underneath. It can't equal minus 4.5 because that would take place if x was equal to 1, which it's not going to be. So the y values of this function are always between minus 5 and minus 4.5. And fourth and final example, we've got y equals 6 over x plus 1. So we know the 1 over x graph looks something like this, where it has a horizontal asymptote of y equals 0 and a vertical asymptote of x equals 0. So that's the 1 over x graph. If I times that by 6, it's going to get just a bit steeper, so maybe more like that. And then if I add the 1 on the end, that's going to shift it up 1 square in the y direction. So my new horizontal asymptote will now be y equals 1 and not y equals 0. And the whole graph shifts up 1 square, so it will now look like this. We don't want the whole graph though, we only want where x is greater than 3. 3 is roughly here somewhere, so I'm only interested in this part of the graph here. So to help me out, I'm going to just erase all of this part of the graph that I'm not interested in, and I'm only interested in the y values here. The smallest that y can be, well, I see it's getting closer and closer and closer towards this asymptote of 1. So I'm going to say that f of x is going to be greater than 1. I know it can't equal 1 because it's the asymptote. The largest value that y can be is whatever this value here is, which I don't know right now. But I do know it's when x is 3. So if I substitute 3 into my function, I get 3. So the y value here is 3. So f of x is going to be less than 3. I know it can't equal 3 because x can't equal 3. So the range of this function, f of x, is greater than 1, but less than 3. So that is the definition of a function. Why we might need to apply domain restrictions so that a rule becomes a function, and then how we can find the range of a function by sketching it out.